in this video, and it's cutting off my stuff there for some reason. Maybe if I like do this or this, I don't know what's wrong with you. Anyways, so I'm going to work through this one more problem, okay? Then I'm going to show you what I consider to be a really, really, really hard problem. I'm not going to do it because we're going to do that really, really hard problem in discussion. And we're not going to do it in discussion until week 4. Okay, so I'm a little ahead of the game recording these lectures. Okay, so I'll read you the problem. Coke, I know you can't read it, but that says coke is an impure form of carbon that is often used in the industrial production of metals from their oxides. I'm not talking about coke like cocaine. Get it out of your minds, you college students. Okay, coke is a real thing. Coke is an impure form of carbon. Okay, that's what it is, right? So if a sample of coke is 95% carbon by mass, determine the mass of coke needed to completely react with 1.0 ton of copper to oxide. Wow, there's a lot going on in this problem. And it's cutting off the reaction. I just noticed that too. Okay, so I'll just rewrite that reaction just so you can see it. It's 2 CuO solid plus 1 carbon makes 2 copper atoms plus carbon dioxide gas, and that is balanced. If I do a quick inspection, right, 2 coppers, 1 carbon, 1 carbon, 2 oxygens, 2 oxygens, so it's all balanced. Okay. So how the hell am I going to start this? Okay. And so now I know you're also thinking, well, Chris just told us to start with the first number we're given, and we have 2 numbers. Okay? Let's refine that rule. Start with the first measurable quantity you are given. Start with first measurable quantity. So when you say coke is 95% carbon by mass, that's just like telling us what coke is. Okay? So whether I have 1 gram of coke or 1 ton of coke, it is 95% carbon by mass. It's just telling us what it is. My actual measurable quantity is the amount that I have, the 1.0 tons. That's what I want to start with. I want to start with what I can physically put my hands on. Even though 1 ton, I could not pick that up or put my hands on that. But all the same, you get the idea, I hope. Start with the quantity that we can like measure or that we can pick up or whatever, right? And I don't expect you to have memorized what a ton is. So we look it up. We use the internet. We use our book. We look up what 1.0 ton is. And we're talking about a metric ton. I probably should have indicated that. 907.185 kilograms is 1 ton. Okay. And I also want to say, suppose if I had 100 grams of carbon, this is another thing I want you to start getting used to when you see percentages, like percent by mass or percent by volume. Okay. So coke is 95% carbon by mass. So suppose I had 100 grams of pure carbon. So if I had 100 grams of pure carbon, how much coke would I have? Or how much, oops, I wrote this backwards. Okay, sorry about that. I wrote this backwards. Okay, if I had 100 grams of coke, that's a K, okay? A sample of coke is 95% by carbon by mass. Then I would have 95 grams of carbon and 5 grams of some other crap. I don't know what it is. I don't care. Doesn't matter. Okay? So this is going to be really challenging for a lot of us to work out. Okay? So always start with what, the starting thing is, coke. Say if I have 100 grams of coke, what's it going to be? Well, it would be 95 grams of carbon and 5 grams of impurities. Okay, so now let's work through this problem. So I'm going to start by saying 1.0 ton. And I know in this relationship, 1 ton is 907.185. I started with this being redundant because what if this wasn't 1.0? What if it was 1.2 or 7.34 or whatever, right? So I just started that 1.0 just so I can keep track of what I'm doing. So 1.0 ton, in 1 ton, there's 907.185 kilogram. So the ton and the ton unit are canceled. I'm going to get us into the gram because hopefully you can recognize I need to get to molar mass. And to get to molar mass, I need my units to be in grams. So I went kilogram, I went down then up. So kilogram and kilogram cancel, and now I've got gram. And what is this that we're talking about? It's 1.0 ton of copper 2 oxide. Okay, remember copper 2 oxide, that's copper 2 plus. Oxygen, oxide is O2 minus, so that's why it's CuO, right? They both balance. I only need 1 and 1 of each. Okay. And so when you go and calculate the mass, the molar mass of copper 2 oxide, it's 79.54 grams per mole. So I've got grams on the top, so when I go down, I need to put grams on the bottom. 79.54 grams of copper 2 oxide is 1 mole of copper 2 oxide. Okay? And now I can compare moles of copper 2 oxide to moles of carbon because it's asking me determine the mass of coke needed to react with copper 2 oxide. I don't have coke in my chemical formula, but I do have carbon. So I can use that for my reaction. I can say, look here, right, go down. I need moles of copper 2 oxide, and I'm going to convert that into moles of carbon. So this is that step where we have to convert moles of one reactant to moles of another reactant. And my balanced reaction says 2 moles of this copper 2 oxide are going to react with 1 mole of carbon. Okay? And I'm going to keep going, folks. Let it ride. Let it keep going. Okay? And let's make sure we're canceling everything. So grams of this canceled with grams of this, and moles of copper oxide canceled moles of copper oxide. So now I need to cancel that moles of carbon. So I'm just going to put this down here and write moles of carbon because that's what I know I need to do. And it's saying what mass. So at this point, I will use the molar mass. Okay? And the molar mass of carbon, 1 mole of carbon is 12.011 grams. All right? This is the hard part. All right? Because now I've canceled moles of carbon and moles of carbon, but it didn't ask me for the mass of carbon. It asked me for the mass of coke. So this is why I wrote this down in the beginning, because now I can easily say, oh yeah, well, if I had 95 grams of carbon, right? Grams of carbon cancels grams of carbon. Then I have 100 grams of coke, okay? That's hard. I realize that's challenging, and a lot of you are going to get stuck on this. If you get stuck on this, come talk to me. We'll work through it, okay? Practice makes perfect. And now I've canceled everything. The final unit I have left here is grams of coke, and that's what I was asked for. So let's calculate it away, all right? I'm going to start here. I'm not going to say 1.0 because I know that I don't need to multiply with that number. So I'm going to start with 907.185 times 1,000 equals times 1 times 1 times 12.01. 12.011, okay, equals, and then times 100 equals. Now I'm just going to leave that in the calculator, all right? And now I can say divided by 79.54, okay? equals divide by 2 equals, and finally divide by 95. Okay, great. And that's 72,100. I'm going to express this in scientific notation, and I'm going to go, move the decimal. 1, 2, 3, 4. And so I'm going to write that as 7.2. And look, the 1.0 means only 2 sig figs. 7.2 times 10 to the 4th grams of Coke needed. Now, I know on that last problem, I was like, well, that was, it didn't ask me for what mass, grams or kilograms. So you were kind of free to choose. So it'd probably be logical to convert this all the way to tons, so I can compare like tons to tons if I wanted to. And so I could certainly do that, right, if I want. So this would be a fine answer, okay? But what if I wanted to compare, apples to apples, right? Well, now I know I can say in 1,000 grams, there's 1 kilogram. And in in 907.185 kilograms, there's 1 ton. And again, I know that this is redundant from what I did before, but I like to do this redundant way of calculating so I can keep track of what I'm doing. Okay? So then I could say divide by 1,000, and then I could say divide by 907.185, and I get 0.080 tons. Okay? So there's a pretty big difference in that mass. And the reason for that is because, look, copper 2 oxide is almost 80 grams per mole, but carbon is only 12 grams per mole. So that's why there was such a big difference there, right? Like if I go back to this lithium hydroxide problem, look, lithium hydroxide is about 24 grams, but carbon dioxide is 44 grams in 1 mole. But I need 2 of these for every 1 of these. So 2 times 24 is about 46. So that 46 grams to 44 grams is really close to that 1-to-1 ratio in terms of mass. It's 2-to-1 in terms of moles. But it came very close to being 1-to-1 in terms of mass because the masses of these 2 reactants are very similar. However, on this problem, copper 2 oxide is much heavier than carbon for 1 mole of that material. So that's why, for every 1 ton of copper 2 oxide, it only needed 0.08 tons of Coke, or 7.2 times 10 to the 4th grams. Okay? So the last problem, I'm just going to introduce this problem, and then I'm not going to do it because we're going to do this in discussion. It's a big, scary problem, but it's related to exactly what I started talking about at the beginning of this lecture, the carbon cycle and combustion and CO2 in the atmosphere. So I'll redo this problem. And by the way, this says 2017. In discussion, I have the 2019 numbers for you. The year 2020 isn't up yet, or maybe the 2018. It takes a few years to get these numbers. But these numbers are accurate, okay? In 2017, the United States consumed 143 billion gallons of unleaded gasoline. That's for real. That's a real number that I looked up. 143 billion gallons of unleaded gasoline for motor vehicle use. Estimate or calculate the number of grams of CO2 the U.S. produced from combusting gasoline in 2017. Okay? That's what you're trying to do. How much CO2 did all of that gasoline put in the atmosphere? Right? It's a pretty simple question. Okay? If we consumed all of this gasoline, how much carbon dioxide did it put in the air? Okay? Simple question, not so simple to calculate it. So here's all the information you need to calculate that. You can assume everyone used the same grade of gasoline, the 87, that's the less expensive stuff, which is approximately 87% by volume octane. So here's like a by volume thing you have to be able to do. And all the octane was converted completely into H2O and CO2 in the presence of O2 upon combustion. So it's basically saying just assume the combustion went complete. Okay? And You need the density of octane too. Octane has a density of 0.7 grams per mil. This is a hard problem, but this is why you're in college, right? To solve the world's problems. So I don't want to waste time with doing these like worthless chemistry problems that you'll only ever see like in your textbook. I want you to be able to calculate real stuff. Like if we consume 143 billion gallons of gasoline in 1 year and only cars, right? This doesn't include boats or planes or turning the lights on, right? Charging your cell phones. This doesn't include any of that. This is just cars. This is a practical thing for you to learn and to be able to calculate. And we're going to do it. And once you learn how to do this, you're going to think that wasn't too hard. Okay, folks. I'll see you in the next video.